the second part of today's lecture. And it's the title in the textbook is Properties of Power Series, but I really call it Working with Power Series. Now, some of this material actually is already in 6.1, and so some of the homeworks of 6.1 are actually about things that I will explain now. Okay, so there are a couple of things that we're going to say about here, and the textbook is, I'm diverting slightly from the textbook, so each video is more concentrating on one particular thing. Okay, so the first thing I want to talk about is, so we now know what a series is. So I remind you, a series is just a power series, sorry, is something that is now given. It's a series where now we have a variable x, and then the question is what values of x can we plug in, and that was the radius of convergence and the interval of convergence that I discussed in the last video. But the question that we now can ask is what are these power series? Do we know any power series? And perhaps some of the functions that we know, perhaps there are actually power series. So all this we're going to answer, not all today. It's going to be takes us a little while, and we're going to do a little bit longer than what the syllabus says. We have enough time, don't worry, to explore all this. So, and today I'm going to only give you, for now, one series, one function that we know that we can write as a series. And then at the end of the lecture you see a couple more. And then the next lecture, I will give you a more general method of finding power series. Okay, so this goes back to the geometric series. So I want to remind you again how that worked. So we have this initial term, right? And then we have this power of, it looks like an exponential function, right? Because r is in the ratio and a is the first term. And then the condition was that if the absolute value of r is less than 1, then this actually is given by this formula. Yeah. Now the a is there, but it's actually really not such an important thing. So I'm going to get rid of my a here. So in other words, a is just 1 for me. And I'm going to look at this series. But notice that there's this condition here, r is less than 1. And this is just a regular series, but I'm going to make it a geometric series very simple by replacing r by x. So we have now the geometric power series if you want, but I'm not going to give that name. This series. So this is just, if we would write it out, what is this? Remember our series we can write out a couple of first terms, right? It's x to the power 0, that's 1, plus x squared, plus x cubed, plus ... Okay. So, we can calculate the range of convergence. We know how to do this by the ratio test. But actually, I can go a little bit quicker here. I can say, look, how do I get this fellow here? Well, it's just by replacing r by x, right? So replace r by x, and that's what I get. But then I can do this here too. I'm replacing r by x in the left-hand side, but let's do it in the right-hand side. And then we get equality. That's 1 over 1 minus x. Look, this is a function now of x. This is a rational function, a very simple one, but okay, we run into it sometimes. And so what we have now shown is that this function that we know very well, rational function, is actually equal to this power series. Okay, so you might think power series are new things, but we'll see many of the things that we know are actually power series. But there's a big caveat. There's a big thing that you have to be careful about. Notice that there is this, I'll box it here in red, there's a condition here. So this function is only works correctly if I replace, now remember, what I did was replacing r by x in both cases here, so I have to also replace r by x here, if x in absolute value is less than 1. Now, turning things around, I'm sorry for this confusion about this r here, but what this means is that we actually found that the radius of convergence, rho, the radius of convergence, what is the radius of convergence of this series? Well, it's 1, right? Remember we said you solve for x minus c less than some number, and that number is the radius of convergence. So here we did this. Notice, by the way, that the center here is 0. So that's another restriction that we have made here. We have this series that we have here is centered at 0. We will later see centers, not today, but next lecture we'll see what happens if we want centers elsewhere. But in 6.2, the center will always be 0. In the homework, sometimes they write it a bit misleading, confusing. So when they say centered at x equals 0, they mean c equals 0, okay? So understand the homework problems in that sense, okay. Now, I said this is radius of convergence, but remember we can actually test this with the ratio test by what we discussed in the previous lecture, so you could definitely do this, try this out. Okay, so that's good. We actually have now a series, and we know that's actually a function, well, at least when the series makes sense. But remember, the radius of convergence is exactly where the series makes sense. You might ask, what about the endpoints? In this kind of questions, we never look at the endpoints, okay? So that's not our issue here. Okay, but now that I figured this out, let's try to do a little bit, perhaps, what about this one? If I would do, I'll write, instead of writing the summation sign, I'll write it here, 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus. So what I'm taking here are the even powers only. Okay. So how does that work? Well, what is this? How do I get, so now we are asking, how do I get from here to there? Right? We started, right, so we used this formula that we had, and then we said, oh, if I replace r by x, I get this fellow. But perhaps I can keep doing things similar like that too. And yes, instead of now replacing r by x, tell me, what should r, in this formula that we have, what is r now? If you look at this series, it's not x, but r here is x squared. Let me write it here. R is x squared, right? So if I replace in my formula r by x squared, I get exactly this, right? Remember this, if I would write this out, this is 1 plus r squared plus r cubed plus etc., right? Exactly as the one below here with the x instead of r. And so now if I replace r by x squared, then, okay, this is x squared now. X squared, well, that's x to the 4th. X squared to the 6th. X squared cubed, that's x to the 6th, right? Remember, you multiply the exponents. So r to the 4th, if you replace r by x squared, you get x to the 8th. You get it? Okay. So, I did this on this side, and I should now replace r by x squared on this side. So 1 over 1 minus x squared. But I should also replace it in here, right? This also, still this condition, so this becomes if x squared is less than 1. So now we have an expression. Can we read the radius of convergence? No, because we have to figure out what, we have to write the absolute value of x less than something. So we have to solve a little bit by this, but actually it's not so hard to see that this is the same as the absolute value of x squared less than 1. And if the square of a number is less than 1, we can take square root of both sides. That means the absolute value of x is less than 1. So yeah, rho is again 1 here. The radius of convergence of this series is also 1. Now let me show you that it's not always a 1, so I'm going to do one similar one. What about this? What about if I now take 1 plus 4x plus 16x squared plus 64x cubed plus etc. So what have I done now? Well, instead of, what is r now? How do I get from my geometric series here to this guy? Let's do another color that we can follow what is going. So how do I go to here? What is r now? I should replace r by 4x, right? Because if I do this, then, okay, that becomes 4x. What is this one? R squared becomes 4x squared, which is 16x squared. This becomes 4x cubed, which means 64x cubed. Okay? All right. So, if we do this on the left-hand side, we should also do it on the right-hand side. So we get equality. This is equal to 1 over, and now r is 1 minus r is 4x. And we should also do it with this condition here. This means if r 4x is less than 1. So what's the range of convergence here? Again 1. No, remember, we have to solve for absolute value of x. We have 4x here, so we have to solve it a bit. So there's 4 times absolute value of x is less than 1. We have to isolate the absolute value of x, so we get absolute value of x is less than 1/4. Cross multiply, right? Or whatever you call it, divide both sides by 4. So what is rho here? Rho, the range of convergence, is actually 1/4. Okay? So this tells me that, what it means now, so let's recap it a bit. So this means that this series here and this function, which is just a rational function, are the same provided x is less than 1/4. Because this series only has range of convergence 1/4. That meaning whatever number I plug in, as long as it's absolute value less than 1/4, this series here converges. Now notice I have not used my sigma notation anymore, but I can do this equally well, right? Summation, remember in this case we replace r by x squared, so it is x squared to the power n, which I could simplify as sum x to n. Okay, so this is now the sigma notation for the same series. So what's the sigma notation for this one? Well, replace r by 4x. So we have 4x to the power n, which I can write down. If I want to separate the power of x, then it would be summation 4 to the power n, x to the power n. Now you can, each of these power series, okay, this one or this one, you could go do the ratio test on and find out what the range of convergence is, and you will get exactly what I just said. Okay, great. That's one thing that we can work with. So this is the geometric series. Now we have not really worked much. What we did, well, what we did is we said we can do substitutions, right? We replace an r by x or an r by x squared, or so on. So now the next thing I want to talk about is, after all, this is calculus, right? So what about derivatives? Okay, so if I have a series f of x, and I'm going to write it now very general. We have a general series here, starting from 0, but remember it can also be from some other index that I start. And with radius of convergence, it has a certain radius of convergence, which I just denote rho. Remember, rho could be 0, which means it's kind of useless, or rho could be infinite, which would be great, because it means no matter what you plug in, the series converges. But in general, it's just some number. Okay, so we have the radius of convergence rho of some series. So what's the derivative? Right? If this is a function, it should probably have a derivative, right? Because at least on the domain of convergence. Remember, the domain of convergence here would be x, absolute value of x less than rho. Notice I'm talking here only about series that are centered at 0, but it works also for functions that are centered elsewhere. I'm not going to do that. It gets a little bit too confusing otherwise. Okay, so before I actually work it out, let's try to see whether perhaps I can figure it out. What would I do? Let's go to a concrete example. We have now a couple of concrete examples. This here. How would I take a derivative of this thing? So let me say. So I'm going to write down the formula later, but okay, so we have this series here. Well, let me just spell it out what it is. It was 1 plus x squared plus x cubed plus dot 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 dot. And we know it was equal to 1 minus x, but only if x was less than 1. The radius of convergence. Okay. Good. So how would I take derivatives here? Well, if it would be, I would take derivatives of each of these terms separately, right? That's how I would take derivatives. Okay, so let's do it. So I'm taking derivative of 1, that's 0, derivative of x, that is 1, derivative of 2x squared is 2x, plus 3x squared, plus, well, let's do one more, right? Because, plus 4x cubed, plus dot 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 dot. Now, that's correct. That's how we will take derivatives of a series. Therefore, because we have an equality, that means this other right-hand side is also, we can also take the derivative of that. What is that? Well, okay, it's perhaps better to write this now as 1 minus x to the power negative 1. So I have to take the derivative of this thing. What is the derivative? Power rule. Minus 1, the opponent comes down, and then we subtract one of the opponent, and then there are, multiply with the derivative of the inside function. There is one, right? Negative 1. It's a bit annoying because this, we normally would write x minus 1, but in this thing it comes out 1 minus x. What are you going to do? Okay, so what this means is, well, the minuses cancel, so I get 1 over 1 minus x squared. Oh, we saw this already, you say. No, you didn't. This is 1 over 1 minus x squared. This is 1 over 1 minus x squared. It's different, right? We cannot distribute the square. And you notice also that the series are different. See, this was the series here that for 1 minus x squared. The series I found now is this one, which also has odd terms. Okay? So you get for free a new series. Namely, this series here is equal to this function. So a new function that we didn't have yet has now a series. Now you could say, yeah, but where? What is the range of convergence? The good news is the range of convergence doesn't change. So this is still for x less than 1. So what is the general case? The derivative? Well, you do derivatives if you would do as if this was just a polynomial. We call them polynomials of infinite degree, so that's why we can do this. Now, what is the derivative of an? You can think about it for an hour and get stuck on it until you realize an is a constant. So it's just a constant. We don't never take derivatives of that. So we only have to take the derivative of x to the power n. That's n to the x minus 1. Okay? So what it means is, rather than writing down this formula, don't write too many formulas down. What it means is exactly what I did here. You take derivatives at any stage of every term. And so this is, again, the radius of convergence of this new derivative is also rho, the same rho. That's nice, right? So so let's do another example here. I'm going to make up a series. Okay, please do this with, for instance, this series. What is the derivative of this series? Note that we know what the derivative should be. It should be the derivative of this guy, which we have to. Well, let me do it. Okay, let me do this one. Okay, I'm going to do it here because I don't want to copy too much. So I'm going to take derivatives. Okay, I take the derivative here, and therefore also the derivative there. If I take the derivative there, I get 0 plus 4 plus 2 times 16, 32x, plus 3 times 64, 180, 192, 192x squared, plus, and I'm not going to even bother what the rest is, equals the derivative of this fellow, which is 1 minus 4x to the power negative 1, so it's negative 1, the exponent comes down, then we subtract one of the exponent and multiply with the derivative of the inside function. You see where this negative 4 comes from? Okay. And what is rho? Well, rho is still the same. Well, rho was a 1/4, so rho is again 1/4. Okay? So here we have a series 4 plus 32x plus 102x squared plus blah 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 equals, we can write this a little bit nicer if you write everything out with no negative exponents and get rid of the negative signs. That's what you get, right? So again, here's a function that whenever rho is less than 1/4, or rather I should point here, rho less than 1/4, it's equal to this series. That's how it works. Okay? Okay, all right, you say, okay, now I kind of can guess what is going to happen with antiderivatives. The same thing. Why not? So I'm going to write this already here. It's easier to keep everything together, right? So the antiderivative of f dx, the indefinite integral, well, what would I do? Exactly the same as what I do with polynomials, term by term. Again, an is a constant, so I don't care about that. And now I add one to the exponent and divide by that exponent. Okay? It's an antiderivative, there is this plus c. We should not forget that. And what about the radius of convergence? Well, what do you think? Nice, right? It's still going to be rho. the same row. So taking derivatives or taking derivatives does not change the rate of convergence. I should warn you, it might change the interval of convergence, but as I said, we're not going to bother ourselves with that. Okay, so okay, I want to take this one again. Right, this is the simplest of all series that I know now. And this row was 1. Or let me write it perhaps in there are two ways of writing that. So I can write it if x is less than 1, and this means that row is 1. I'll write it this way. Okay, so I'm going to take antiderivatives. So I'm going to antiderive here. Okay, so the antiderivative of 1 is x. The antiderivative of x is x squared over 2 plus x cubed over 3 plus x to the 4th over 4 plus dot 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 equals, because if I antiderive here, I can antiderive there. What's the antiderivative of 1 over 1 minus x? Ah, that's an ln, right? It's ln of 1 minus x, minus, why? Think about this. Because I have to compensate, right? If I antiderive this thing, the antiderivative of 1 over x is ln of x. But the inside function is 1 minus x. If I take the derivative of 1 minus x, I get an extra negative. So that's why I have to put this extra negative here. Plus c. That's a bit annoying, right? This plus c. Okay, here I have a series. Here I have a function that I kind of know. What is this stupid c doing there? Well, as often the case with these integration constants, we can determine them by the so-called initial condition. So what is our initial condition here? So the initial condition to determine the integration constant, to determine the c, it's not a center, but the c of integration, right? How do we do that? Well, the initial condition for us is exactly x equals 0. That's more generally, again, I concentrate on series with center 0. If you would be a series of center different, then that would be the initial condition. The center is the original condition, but this is 0 here. Okay, so what does this mean here? This means if I plug in, so let's do another color. If I plug in 0 in here, what do I get? Well, obviously 0, right? What I get if I plug in 0 here? If I plug in 0 there, I get minus ln 1 minus 0, oh, that's 0, plus c, because there's a c still. And they are equal. Oh, this tells me that c is 0. So we see that c is 0. But be careful. Just because in this case c is 0, it could be in another case, it might not be 0. Okay, so you always have to check afterwards. If you have a new function here, what is the integration constant that you get? And I repeat here, what about rho, the interval of the range of convergence? It remains the same. So this is again under this condition. That doesn't change, right? That's what I said here, right? This range of convergence is always the same in whether you take derivative or you take antiderivative. But this is kind of interesting because now we have actually all of a sudden a totally new function, namely this function here, minus ln 1 minus x. Okay? And that might not be the function you're really interested in, but it is at least a bit more serious function, right? The other one was just rational functions, yeah, who cares? But this one is already getting a little bit more complicated. Okay, so I can now combine these two things. So let me show you what I mean with that. So now, suppose I am saying, okay, I have this, but I really, really, really would like to have a series for this one. So can I find a power series for this function? Not for all x's, but for x's in a certain range, namely given by the range of convergence. So what's the difference here between what I have, the blue one that I have, the circle blue one, and the one I want? Well, first of all, the negative sign. But that's not the only thing. Remember, look at what happened here. This x has become an x squared. So what we get is that x, we replace it by x squared. We have done this before. We always were doing it on the left-hand side and then changed it in the right-hand side, but now we're doing it the other way around. We changed it in the right-hand side, so we replace this x by x squared, so we should also do it here. Yeah, perhaps I'm going to realign my things a little bit, okay? Give me, otherwise it's too much crossing lines here, right? Okay, so should delete this then. Okay, so I'm replacing here x by x squared, and I get ln 1 minus x squared. Well, I have a negative sign here. Okay, we don't want that, so I'm going to take the negative sign already to the other side. So I'm going to have a negative sign here. This is what I did, right? I took this negative sign and I multiplied it to the other side. If there's a constant, I would have multiplied it with some factor, I would have done something else, right? So, but not only have to change the sign here, but I also have to change this x into an x squared everywhere. So in the first term, this becomes x squared. In the next term, x to the fourth over 2, right? Remember, what's the next one? X to the fifth or x to the sixth? You multiply, it's a x squared to the power 3. You're multiplying exponents, so x to the sixth plus x to the 8th over 4 plus dot dot dot. So the only thing I did was in this expression replace x by x squared, which I did also here, and therefore the two are the same. Remember that c was 0, right? We already found that here, so we don't actually have this guy. Here we are. Now I have a series for this function, ln of 1 minus x squared. And this is the series. Nice, right? And this is for still the same condition. This condition doesn't, well, no, sorry, no, I was a bit too quick here. What's the condition now? Okay, sorry, we have to check the condition, right? Because also something might change there. We're using purple, okay, so in this condition, where is my condition here? Well, I should write it down here. So here the condition was of x less than 1, right? This is the row because 1. This condition, what is the condition now becomes? This condition becomes if x squared is less than 1 natural value. But we have already seen that we can solve this as x squared less than 1, then take square root of both sides, and we get actually this. So here rho is the same. Okay? Alright. But it could change, right? So let me do another example. What if I would replace... okay, I'm not going to work it out, but now ask yourselves, I'll do it very quickly in a different color. Suppose I don't want x squared, but I want 4x squared. Well, why not, right? So instead of replacing this x by x squared, I should replace it by 4x squared. What changes? Well, this has changed, but here should also change. Now I should replace x by 4x squared, and then x squared becomes now 4x squared squared. So that's 16 x to the fourth. And now we have to take here the third power of 4, 64. And the fourth power of 4, which is 256. Okay? Right? We're replacing now x by 4x squared. This is what you get on the left-hand side. This is what you get on the right-hand side. What do you get here then? Okay. This is now the condition. Okay, I'm going to erase now what we have here. Let's work it out what this means. This means here that we have 4 times x squared less than 1. We can still take square root of both sides, but the square root of 4 is equals 2. So 2 of x less than 1. So x less than a half. So rho has become a half. Okay? So you see, when you take derivatives-oriented derivatives, the radius of convergence does not change. But here we're doing something else. We're doing a substitution. And then the radius of convergence might change. Okay? Depending on the substitution. Okay? Now, I want to go back to the one that I had. So I'm going to get rid of all my green stuff. Let's see if I can do this without deleting too much stuff. Oops, I got a list of one thing, but most of it I got. Okay, so go back to the one that I had here. Okay. This was x less than 1, right? So we had, let me just, we had calculated this was less than 1. Okay, let's get rid of these things now. You can always go back in the video if you want to see what was there. Okay, I want to go even one step further. I want to do this here. The antiderivative of 1 minus x squared dx. Now, this is where things are getting interesting, because if I would have give you this integral a month ago in the chapter on integration, you might have been pulling your hair and scratching your head forever, because there is no good method of solving this. In fact, this is an example of an integral that we cannot solve by formulas. We don't have a formula to write down what this integral represents. We know it exists. We know that all these functions have antiderivatives, but we cannot write it down. Well, up to now somehow, because we can still take the antiderivative of this side. Okay, again, I guess crossed my wires again. So allow me to rewrite it again here. I write it. I'm going to write the antiderivative here, right? So I'm going to write here ln 1 minus x squared dx. Okay, antiderive here, so I do it here too. And that's now very simple, okay? We have this negative sign that distributes. What is the antiderivative of minus x squared? Well, you add 1 to the exponent, divide by it. And then remember the minus sign is everywhere, right? So now we had x to the 5th divided by 5, but already had the 2 here, so 2 times 5. Okay, let me do the minus sign. Let me distribute the minus sign in case that you get nervous here what is going on. So I'm going to distribute the minus sign here. Okay, and now I antiderive. So let's do the next term. That is minus 1/3, and the antiderivative of x to the 6th is x to the 7th over 7. And the next one, minus 1/4, x to the 9th over 9. Okay, and of course, I mean, here you can combine these denominators, but who cares? So here we are. We have now an antiderivative. Of course, this is one antiderivative plus c, I should write, right? But anyway, I have a series here that represents this function that I otherwise do not know how to deal with. And moreover, well, no, I shouldn't say moreover. Only, of course, when x is less than 1 here. So if the absolute value of x is less than 1. But for instance, now I go even a step further. Suppose I say I want to calculate this between 0 and a half, the direct integral. Well, I have the fundamental theorem of calculus, and because I have a function here, now there is an issue. I'm plugging in a half and 0. In fact, this whole interval should be here within the range of allowed things. So perhaps now it's a little bit better to show me to say the interval of convergence, right? You can go 1 to the left or 1 to the right. That's what rho equals 1 means. So rho equals 1. And the center is 0, so you can go up to there, up to there. Now the interval that I want to integrate with is this integral. So is this integral, right? Interval from here to halfway to half. Which is entirely inside the interval of integration. Well, I should makes it green, I guess, because that meant that you can integrate over it. Sorry. Okay. So I'm allowed to do that. You know, just what I'm trying to say is, okay, once I plug in points that are within the interval of convergence, I can use the fundamental theorem. So this means now I'm going to take this function here, minus x cubed over 3, minus x5 over 10, minus x to the 7 over 21, and let me only do 3 terms. And now, so there's more here, plus, plug in 0.5. Now, plugging in 0 is easy, I have to plug in a half, so it's minus a half cube over 3, minus a half to the power 5 over 10, minus a half to the power 7 over 21, plus dot, minus, well, don't plug in 0, but that's all 0. And that is, so let me no longer write this anymore. So this is now equal to this integral. So this is a method of solving definite integrals. Because we have a series here that converges, we know that. We don't know what the value is, but we can use it to approximate, right? Remember, what this means is that if we start adding up all these terms here, the more terms we add up, the better the less our error is, the closer we get to the actual value of this integral. So this is a method of solving definite integrals of functions that you otherwise cannot integrate. Okay, there is unfortunately one more topic that I have to discuss. So we had the integration, addition of series, that is very obvious, but I have to talk about multiplication a little bit. There's nothing weird going on, it's just multiplication. It's just a little bit strange is because we have now infinite many things. So I'm going to give you an example. Suppose I have to multiply, I'm going to write down series, and from now on I'm just going to write series down by writing down the first few terms. This is something I will allow you to do in these kind of calculations, right? You see, I always have written down a few terms. In the book, they sometimes you can actually work out the whole thing with the sigma notation, but it gets very cumbersome. And I am not going to insist on that. So, okay, so here's my series that I want to look at, plus x to the 8, plus dot, dot, dot. The dot, dot, dot here is vague, because I have no clue what the pattern is. But this is, I believe, I have some series here. And I want to multiply this with the following series. I'll write it a little bit here. X plus x squared minus 3x to the 5th plus x to the 7th plus dot, dot, dot. Now, of course, I cannot, so this is multiplication. Let me write this big dot. Since I write dot, 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 I cannot write everything down. So let's work out up to degree 6. So let's work down, so these two series now we want to multiply and write down what is up to degree 6. What you have to do is what you expect to do. You have to distribute. But of course, foiling, it is 2 terms by 2 terms. Right now we are talking about infinite many terms times infinite many terms. You see where the issue comes in? So we're going to have to be very, very systematic about this. And so the way I do this, there are other ways, but the way I do this is I look at, determine what the various coefficients will be of the powers of x. So we have this, the power of x, so x to the power 0, which is just the constant, x to the power 1, which is just 1. Then we have x squared, x cubed, x4, x to the 5th, and x to the 6th, we said, right? Let's work it out this way. So I'm going to kind of make it a bit of a table here. What I'm going to try to find are the coefficients of these powers. But I'm writing the table this way. You can write it horizontally also, but space-wise it works better. Okay, so what does that mean here? So here this is the constant, right? So I'm looking now, in this product, can I form a product? So what I'm going to do is pick a term from here, so this one, and a term from here, and multiply together. Now what you get, you see, is power 6. So this will contribute in this line, okay? But not, because that's 6 power, okay? So let's just, if you just pick randomly and start multiplying, you are bound to miss something. So I'm not going to do that. So what I'm going to do is work very systematically. So I'm going to look first at, can I get a power constant? If you think about it, no, because here it's at least a power of x, and here is at least a power of x. So in fact, you cannot get anything here, and also nothing there. There's no way you can form just a single power x, right? It has to be at least x squared. So let's x squared. What are the ways that I can form x squared? There's only one way. Okay, I'm going to use a lot of colors. So let's get myself. Okay, let's do green here. What is the way to do x squared? There's only one way. This x with this x. What's the coefficient? 1 times 1. So a 1 here. And that's it. There's no other way I can make x squared. That's it. Now x cubed. There's perhaps a little bit more I can do. I'll do x cubed here. So x cubed. If I multiply this x with this x squared, I get x cubed, right? And what are the coefficients? Again, 1 and 1. Is there any other way I can do this? Well, the safest is to walk to the first one, say. Can I combine this x cubed with something? Unfortunately not, because if you multiply with any of these terms, you're going to have at least a higher power. So that's the end of the story. Okay. Move on to x to the 4th. With this x, can I combine it somewhere here to get an x to the 4th? I would have to combine it with x to the 3rd, which is not there. So I get a 0. This one gives me 0. Can I combine this into an x to the 3rd? Yes, I can. Namely, with this x. Now the product of the coefficients, here the coefficient is -1, here the coefficient is 1, so the whole thing is -1. Okay? Look, I'm listing them all, everything I can get. X to the 4th, anything else? Can I use this? No, because any power here is going to make it bigger. So that's the end of the blue, of x to the 4th. But you see, the higher the powers are, the more combinations there are going to be. X to the 5th. Can I combine this x with anything here to get x to the 5th? No. What I should have is an x to the 4th, which is not there. So that gives me 0. What about this guy? Yes, this combines with this one. So we have now this -1 together with the 1 coefficient here. So this is -1. But there's another one. Look at this, x to the 4th. I can combine this with this x to get to this x, to x to the 5th. So this would be, what? Now we multiply the coefficients, 2 and 1. So I get a 2 here. Okay, sorry, let me, a 2 here. Let's go one further and then I'll say what, I haven't wrapped it up yet, but I'm going to first show how things work. X to the 5th. Oh, sorry, no, that's not what I want to do. Sorry, here, x to the 6th, sorry. Okay, let's go again. Let me get a little bit rid here of this bottom part, otherwise too much colors, too much rainbows. Okay, so can I combine this x with anything over here to get x to the 6th? Yes, I can. I can combine it with this guy. So what I get is a -3. How do I get -3? I multiply the coefficient in front of here, which is 1, and the coefficient in front of there is -3. You got that? Okay. This x cubed, can I combine it with something to get an x to the 6th? Unfortunately not. So again, this is going to give me 0. Can I use this x to the 4th to combine it with something? Yes, I can, namely this x squared. That gives me x to the 6th together, and the coefficients are 2 and 1, so I get a 2. What about this x to the 5th? I can also combine this with this x, and now I multiply the coefficients. It's 2 times 1, so another 2. And that's the end of the story. So what do we do with these coefficients? Well, we add them up, right? Because in a distribution is you multiply all the terms. And so what I wrote down are all the like terms here. The like terms x to the 6th, and they come with coefficients -3, 0, 2, and 2. So it means I have to add them all up. So I take the sum here. So of course the sum, let me do everything in black now. Sorry. This is just 0, this is just 0, this is just 1, this is just 1, this is -1, this is +1, -1 plus 2 is +1, you get 4 minus 3 is 1. So what this means is that this product is equal to 0 times x, so I write it up, 0 times x to the power 0, plus 0 times x to the power 1, plus 1 times x to the power 2, right? Plus 1 times x to the power 3, minus 1 times x to the power 4, plus 1 times x to the power 5, plus 1 times x to the power 6. So I get x squared plus x cubed minus x to the 4th plus x to the 5th plus x to the 6th. Now for some reason all the numbers were 1 and minus 1 and so, but that's not the case in general. So I'll do one more example and then I'm gonna assign homeworks. So let's do another multiplication here. Let's multiply 1 plus 2x minus 3x cubed plus x to the 5th plus dot. Let's multiply that with x, 2x minus x squared plus x cubed plus x to the 4th plus x to the 7th plus dot dot dot. No, let me make this a 2 here also, and I want to go up to x to the, so okay, let me put one more term here, plus 6 times x to the 8th. So let's do everything up to degree, again, up to degree 6 again. It's a lot of work, but I want you to see how things work, okay? So we have the powers, x to the power 0, x to the power 1, which is x squared, x cubed, x to the 4th, x to the 5th, and x to the 6th. Okay, x to the power 0 constant. Can I make a constant here? Well, again, I'm going to use my first one and walk through the various powers in increasing order. This one I can combine, but whatever I combine it here with, it's always going to be at least a power 1 or higher. So that doesn't work. So the result here will be 0. Okay, what about, let's use our colors, right? What about x? Are there ways of making x? So I'll start here. With this one, I can make an x together with this one. Multiply the coefficients, I get 2. Is there any other way? Can I use this one, for instance, with something? No, from now onwards, the things would be too high. So that's the end of the first power. Okay. What about x squared? With this one, I can combine with this minus x squared. That will give me a minus 1, right? Multiply the coefficients. Be careful, we are multiplying the coefficients here, right? What about this 2x? Can I get an x squared? Yep, with this one. And this, what's the coefficient here? Multiply the coefficients, so I get 4. Can I use this to get x squared? No, obviously not, it's too big. So, okay, that's the end of x squared. So what about x cubed now? Let's go green. The 1. Can I combine it with something? Yes, with this one. The coefficient, product of coefficient is 2. Can I combine this with an x cube to get an x cube? Yes, with this one. The coefficient would be negative 2, right? Can I combine this one to get an x cube? No, unfortunately not, because if I multiply with anything here, it will be at least power 4. So that's the end of x cube. Okay, let me get a little bit of these colors here. Oops. What was this? Now I got lost what this was. That was 2x, right? Right, let me, I cannot redo. That was 2x, right? 2x, right? Okay. Yeah, from the first term I can see that 2x. Okay. Sure. Now x to the 4th in purple. Can I combine the 1 with what? I can combine it with this x to the 4th. So 1, product of the coefficients. This 2x can be combined with this 2x cubed. Product of coefficients, 4. This minus 3x cubed can be combined with what? With this 2x here. To get x to the 4th. Product of coefficients, negative 6. Remember, it's a product I'm taking. A product always of the coefficients, right? If you work this out, it would be like I'm expanding this, right? I would multiply this term. What I'm doing is multiplying this term with this term. And the result of that is you multiply the coefficients, and then you multiply the powers, x times x to the cubed, which is x to the 4th. Okay? Good. Let me get rid of these boxes here, because otherwise I get too much. Can I use x to the 5th? No, I cannot. Okay, so next one, blue, x to the 5th. This one combines with this one. No, that's the 4th power. There's no 5th power. Okay, so it doesn't work. So 0 there. Can I combine this 2x with something? Well, yeah, I can combine it with this guy to get it fixed, so to get a 2 here, product of the coefficients. What about this guy? X to the 5th, I should multiply it. What am I doing? X to the 5th, right? Yes, so I have to multiply it with this guy. Minus 3 times minus 1, that's a 3. And then this x to the 5th, no, that won't work. So nothing else anymore. So that's the end of the 5th power. And then finally, the last power, I'll do it in brown. X to the 6th. I cannot combine it with anything here, right? So that's going to not give me anything. What about this term? 2x? Nope, doesn't combine. Does this combine? Yep, it combines with this one. No, with this one. Sorry. So wait, let me get rid of this thing. So it combines with this one here. X to the 6th, right? So minus 3 times 2, that's negative 6. This guy, does it combine with something? Yes, with this. This gives me 2. And then, again, I'm too high. There's nothing else anymore. So I'm done. And so what are the coefficients again? 0, 2, 3, 0. Now I'm adding coefficients, okay? So it might be a little bit confusing. When I calculate the coefficients, they are products. Then when I have all the powers, I'm adding the like terms. It's adding the like terms I'm doing now. So now I have 5 minus 6 is minus 1, and then 5, and then negative 4. So this means no constant. The constant, the power x has coefficient 2, 2x, plus 3x squared, plus 0x to the fourth, minus x to the, 0x to the third, minus 1x to the fourth, 5 times x to the fifth, so plus 5 times x to the fifth, and then minus 4 times x to the sixth. Okay, so there are no good homework problems on this last topic, so I'm going to put some extra homework problems, and the other ones I will just list on the website. So work out for me this. Which one did I do here? Let me see. I have written down one. I want to make sure I don't give you the same thing we did already. We did. Oh, okay. Let's do this one. Okay. So calculate here 1 plus 2x plus 4x cubed. 4x squared plus 3x cubed plus x to the fifth plus x to the eighth. Multiply this with 2 plus 3x plus 5x squared plus 6x to the fourth plus x to the seventh up to degree, let's see what I wanted you to do, up to degree 6. Okay, it's a bit more work, it's a little bit longer problem, but if you do this, if you understand what is going on, then you probably will get this, it won't be too hard. Okay, so do this extra homework problem. I'll also give the solution of it later, and then the other homework problems I will assign.